So, as you know, we're mostly made out of water. Life is dependent on water. All life that we know of, at least as far as the definition of life exists, as it exists now, is pretty much based on water. So we need to be really familiar with the water molecule. So you can look at here, and you can see how you have the oxygen, and then kind of off to the sides you have these hydrogens, what's called a bent molecule. And what that does, it makes these charges slightly negative on that oxygen side and then slightly positive. You can see that right here, these hydrogens slightly positive, the oxygen slightly negative. As we all know, opposites attract. And that's going to give water a lot, sorry for the handwriting, a lot of interesting properties that is fundamental to why it's so important for us. And let's get into that. So we got capillary action based on cohesion, something called surface tension and adhesion. We'll go through this in a second, but cohesion, sticking together. Surface tension, we have that layer of water. You might have seen, I should have a picture of it here, but water skippers can stand on the water because the molecules bond so tightly, their legs don't have enough force to break that bond. So a lot of things can sit on the surface of water because of that tension. And then adhesion, water can stick to other things. Like you throw it on the wall, it'll stick. And you can see that if you stick like tubes in water. Right here, you can see it going up against the pull of gravity. And you may notice this water is going up higher than this water. That's because the vessels, say in a plant, this could be akin to the xylem vessels that plants have. The closer the walls are together, the more that water can grip and kind of pull its way up via what's called transpiration force. When the water evaporates from the leaf, helps it give a slight tug on all these water molecules and pull them up the plant until it gets to a nice leaf where photosynthesis happens. And that water then goes into the air. And you see in mercury over here, you actually have the opposite effect. It doesn't want to, it's actually polar. I'm sorry, non-polar. And water being polar, it has that uneven charge and it can grip and hold on to stuff. So, as I mentioned before, water sticking to itself, cohesion, you kind of use a colloquial term for this, it works well. That makes it not want to lose a grip on itself, so it doesn't evaporate very easily, but when it does, it allows more heat to leave the body, and it works as a good coolant. And like I mentioned before, it allows the water to be pulled up, plants, the xylem tissues, those like the blood vessels in a way for plants. Plants have two vessel systems, one just for water and then one for sugars and proteins that it makes. It's interesting because water goes up the vessels and then sugar comes down the vessels, like two-way street in separate little tubes. Adhesive means it sticks to other things. That also helps the water to move up plants to get to the leaves where that water is required for photosynthesis. Thermal allows water to cool you down well when it evaporates. Creates a steady, keeps a steady temperature, that high specific heat. All these organisms, all these living things in the oceans and our lakes don't really have to worry about heat management because the heat can easily move along to the water surrounding it, and the water stays at a very constant temperature. It doesn't fluctuate by much ever. And the solvent properties, meaning things dissolve well in water. And you need stuff to dissolve in water if you want chemical reactions to happen. You want those chemicals, enzymes, substrates to mix together and come into contact, and that's not going to happen unless you have some medium, some kind of solvent, and water does that really well. And that's one of the reasons why most of our cells are made out of water. So a couple pictures here. As you can guess, this person is sweating profusely. He got the armpit sweat. You see all the sweat dripping down from the face. So this is, as a coolant, that high specific heat, helping to get that heat energy radiated to the atmosphere away from the person, so the enzymes don't break down and the reactions can continue well. And here, probably the the shark and other organisms living in the ocean, thermal stability. So we have, the water temperature not fluctuating too much. And over here you have water boiling. Again, that high specific heat takes a lot of energy to boil the water, and that allows it to help us to manage our heat. So here's a little cartoon. Hydrophobic and hydrophilic. Those are some terms I think all of you are understanding. Maybe not philic, but definitely phobic is a fear. Yeah, phobias. Philos, I think that's the Greek root, but is love. Like Philadelphia, city of brotherly love. Okay, so hydrophilic, hydrophobic. Make sure that doesn't, those words you understand. So here we go. If you look at your blood and you let it settle or put it in a centrifuge, you'll find that it's about half water, half solid, which is really weird. We think of our blood as being liquid, but there's a lot of solid cells in there. And in the liquid part, you have a lot of molecules, dissolved amino acids, sugars, lipids are floating around in there. Some proteins are soluble and they float and they dissolve in there. Otherwise, they're suspended in there. But it has kind of does that some people have real trouble looking at blood even in a circumstance like this. I'm not the best, but if you give blood, you'll get up close to all of this sort of gear and seeing the blood there. So I mentioned it is a bent molecule. Water is. And you need to understand the differences with methane. So comparing water and methane, that's one of the requirements of IB. And you'll see the uneven nature. You got the slightly positive. This symbol means slightly. Not doing a very good job. What does this look like? This equals slightly. I'll put slight. Okay, and then methane has this tetrahedral shape versus bent shape. And again, this would be non-polar. This would be polar. And, make sure you go through this and you're able to, pick up on these differences. Definitely the formula, just the carbon and 4 hydrogens, water, you all know well. Mass is pretty similar, but look at the density. Methane is about half as dense as water. And also the specific heat is much lower. It'll change states a lot more easily. Same thing here, 760 joules per gram, 2,000 joules per gram. And of course the melting and boiling point are different, based on those differences. I think this is a really cool picture. Here you have just nothing. No life, not even, most weeds. You look around, there's really dry areas, dry hills on the way to Las Vegas or someplace. You will still see some kind of plant clinging to life. You look at concrete, sidewalks, you will see little plants poking out. In dry areas, you'll see plants sustaining. But here, even those dunes, there's nothing. But right where you have this oasis or this river, you have all this vegetation. So this is just a really cool picture. I think it's real. Almost looks Photoshopped now that I think about it. of this this oasis, and this just the difference between what water does. This would be the planet most likely without water. This is what it looks like with water. Completely different places. Think about it. So the three states of water. So solid we have right here. You got liquid. And you might say the clouds are gas, but that's actually also liquid. And the thing is, you can't see vapor. So you can't see the three states of water here. You can see, so you can't see three, but you can see two states of water.